Thank you very much to the organizers for giving me the opportunity to speaking today to you about the work that we do in our laboratory, and in particular about plasma emission spectroscopy and the role that it has in the study of the origin of the heavy elements, that importance that has in astronomy and astrophysics. Well, our group is based at the University of Valladolid in Spain. Valladolid is a city you can see here in the map. We are in the central part of Spain, not far from Madrid. It's an hour ago in a train. And we have one of the oldest universities in Spain. It was founded in 1241. You can see here different images of our city. It's a city with a lot of history. It was the capital of Spain for a while also, before it moved to Madrid. And well, I invite all of you to come and visit us. It's very easy to reach us from Madrid with the fast trains now. We are the Atomic Spectroscopy Laboratory. We are based at the Faculty of Sciences of our university. And what you can see here is what is the permanent members of this group. This is myself as the laboratory leader. Then we have Pratyush, he is our third year PhD student. And then Professor Santiago, he is the person who founded the laboratory. Now he is retired, but he works a lot with us and helps us a lot. At this moment, we are funded by the Spanish government, and here you can see an image of our faculty. We are a bit in a new campus outside the city. Very briefly, so that you can have an idea of the history of our laboratory. Our laboratory started in 1975. It was created by Professor Santiago. And when he retired in 2018, the laboratory closed, which is something that is happening in many laboratories, sadly. So I was the last PhD student in the laboratory, and then I moved on to the spectroscopy group at Imperial College in London, where I work as a postdoctoral researcher for 5 years. And then I secured some funding from the Spanish government to bring back to Spain researchers that were working abroad. So I think this would be of interest also in this conference. So we reopened again our laboratory in 2021, changing slightly the aim, the measurements that we are doing, so that we were measuring the things that are most urgently needed. And also I was basically moving into doing a bit the work that I was doing in London. So now you can see it's not only the three of us, we also work with many undergraduate students. They are students of physics, and we are putting a lot of effort in attracting and training new students, and also establishing new collaborations for international to improve international mobility and also to get new funding. We also have some international collaborators. Our main collaborators is the group led by Professor Juliet Pickering at Imperial College in London. We also work with the group of Henrik Harman at the University of Malmo. You'll hear tomorrow a talk by him. And also with Gillian Nave. She was the person in charge of the experimental laboratories at the National Institute of Standards and Technology. She's now retired, but continues working as a guest researcher. So what do we do in our laboratory? Well, we are interested in measuring high quality atomic data that are needed in astronomy. Why do we want this data? Mainly because we are trying to answer questions such as what are stars made of? We want to study chemical abundances of different astronomical objects. We want to do studies of galactic archaeology to know how the universe has evolved and what impact this has in composition of different stars. And nowadays we are very interested in trying to answer a very important question, which is what is the origin of the heavy elements in the periodic table? So as you know, the majority of the information that we receive from our universe comes in the form of radiation. And in particular with the stars, we have the core of the star is emitting radiation as a black body. So we have all possible wavelengths. But this core, this star has an atmosphere with other elements, which is colder, as a plasma but colder. And it's going to have different elements. And these elements are going to absorb part of the radiation. And finally, what astronomers can see is what we have here, which is an absorption spectrum. So this spectra gives us loads of information about the composition of the atmosphere of the star, but we need to be able to analyze that. What do we need to analyze the spectra? What do astronomers need? Here we have another example of an spectra. This is from a white dwarf. And if you see what astronomers want to know here is they're interested in positions of spectral lines, because this gives them information about the atomic element that has created that spectral line, and also the intensities of these lines. So to obtain information about positions and intensities, we need two main atomic parameters. This is wavelengths and the so-called transition probabilities. And this is the parameters that we measure in our laboratory. Over the years, a lot of effort and a lot of money is being invested in creating bigger and better telescopes, spectrographs, and detectors to obtain these astronomical spectra. So here I like this image because you can see in comparison the size of the Colosseum in Rome. Then you can see the very large telescope in Chile and the extremely large telescope, which is now being built in Chile also. And you can see that a lot of money is spent to build these instruments, but once astronomers get spectra from these instruments, they are going to go to a database, for example, the NIST Atomic Spectra database, and they are going to look for information about spectral data for different elements. Let's see that, for example, if they are interested in neodymium-3, this is doubly ionized neodymium, this is what they would find. No lines are available in this database. This is the dreaded message for the astronomers, because they got the spectra, which is very expensive, but they cannot analyze that spectra because they don't have the necessary atomic data. So this is what we do in our laboratory. We basically fill atomic databases so that astronomers can analyze their spectra. If we look at this periodic table, this is a very beautiful one in which we are wondering about the origin of the different elements. And here you can see lots of elements that are marked in orange. Well, all these elements are, in theory, produced during the merging of neutron stars. And I say this because the origin of the atomic elements, the chemical elements up to iron is more or less well known. But when we go to heavier elements, there are theories about how these elements are synthesized in the universe, but we still need experimental proof. And this is what happened in 2017. During 2017, it was the first time that the merging of two neutron stars was observed. And it was observed in two different ways. It was observed as a gravitational wave. And then it was also observed in terms of radiation. This is, they observed the emission of the radiation emitted during this merging. And this is what is called a kilonova. You can see here in this plot, in the y-axis, we have intensity of radiation, and in the x-axis, we have wavelength. And we can see this is the emission after the merging of these neutron stars. We can see how it has emission in the UV and optical ranges. But then with these, the emission changes into the infrared. So if the fingerprints, basically, of heavy elements is discovered in this kilonova emission, then this is proof that these heavy elements are synthesized during these events. But for that, they need atomic data. And this is the problem they are encountering, astronomers, that when they go to the databases, the atomic data they need to analyze this, the spectra is not available. The quantity and the quality is very far from the current needs. So this is what we are doing in our laboratory at the moment. We are focusing on measuring heavier elements, and in particular neodymium that you have here in the rare earths. So we've said we mainly measure wavelengths and transition probabilities, but what are transition probabilities? So if we think about two energy levels for an atom, a lower energy level and an upper energy level, we can see that we have three possible processes between these energy levels. We have absorption, and then we have two possible emission processes. This could be a spontaneous emission and a stimulated emission. The one we measure in our laboratory is this spontaneous emission, which is characterized by this transition probability. As you can see, the transition probability is basically the inverse of the lifetime of the upper energy level if there is only one possible transition from the upper energy level. what do we do in our laboratory? Basically, we need to obtain spectral lines, spectra. And once we have these lines, we fit them to mathematical functions to obtain the wavelength, the central wavelength of the line. We are also interested in the full width at half maximum. And finally, this thing that is marked in yellow, the area under the profile. This is what we are going to call the intensity of the spectral line. And we can see that the intensity of a spectral line is directly proportional to two things. This transition probability in red, which is the parameter we want to measure, and also this N, this is the population of the upper energy level. So basically in green is what I can measure in the lab, the intensity, and in red is what I want. But the question is, what do I do about this population of the upper energy level? And here is where we have two approaches, both of which we use in our laboratory, depending on the case that we have in hand. So we can do two things with this population of the upper energy level. We can assume that we have some kind of thermodynamic equilibrium, in which case we can model that population with the Boltzmann distribution. And this is the method that we use when we are using a pulse discharge lamp in which we have some kind of equilibrium. And this is the approach we use for noble gases in particular. But now for the neodymium, we cannot assume equilibrium because there's not equilibrium in the light source we are using. And therefore, the solution is to eliminate. If there's a quantity we don't know anything about, the best thing is to eliminate it if we use the formula in an intelligent way. And this is the method that is called the branch infraction method. I'm not going to go a lot into this method because tomorrow Henrik Harman will probably speak about it. But very briefly, for this method, what we need to do is to measure all the transitions that are coming from a given upper energy level. So there will be, for example, 3 allowed transitions to 3 possible lower energy levels. And we need to measure the spectral lines coming from all of them. This is one of the limitations of this method because one line might be in the infrared and the other line might be far in the UV, for example. Once we measure this intensity of lines, we define what is called as the branching fraction, which, as you can see here, is basically a ratio of intensities, the intensity of one line over the addition of intensities of all the lines. So this is a quantity that we can obtain from our laboratory. And then we have to use this expression, as we saw, that the lifetime is the inverse of the transition probability. But if we have more than one possible transition, we have to do the addition of all these transition probabilities. Okay, finally, we are interested in this transition probability, and we obtain it by combining these branching fractions and the lifetime. One of the problems with this method is that we also need to measure lifetimes. This is measured in a different laboratory, and sometimes it's not possible to measure them at all, and we need to use theoretical values. So this is an image of our laboratory. As a general overview, we are able to measure neutral, singly, and doubly ionized elements in a spectral range between 190 and 800 nanometers. The resolving power of our instrument is around 3 picometers. So you have basically 10 to the 5 in resolving power. And we also have a Fabry-Perot interferometer with which we can go up to 10 to the 8 in resolving power. Our experimental setup has 2 main blocks, we can say. First of all, we need to generate the radiation, and for that we need to use a lamp, what we call a lamp. And secondly, we have to analyze this radiation to obtain spectra. In terms of analyzing the radiation, we use a diffraction grating spectrometer, a 1.5 meter Czerny-Turner, equipped with a diffraction grating which has 2400 lines per millimeter. We can also, if we need higher resolving powers, we can use Fourier transform spectrometers in the labs of our collaborators, for example, at Imperial College in London. And we also have our Fabry-Perot. What does happen in terms of the lamps? What light sources do we have? Well, we have 2, a pulse discharge lamp. This is a lamp that creates plasmas that last for 200 microseconds. This lamp was designed in our laboratories that it has local thermodynamic equilibrium so that we can do some assumptions about equilibrium. And we get temperatures around 30,000 Kelvin. You see, we use these charges of up to 8 kilovolts. But the lamp that we are using currently to measure neodymium is a hollow cathode lamp. You can see here an image. This is a continuous light source. So we can measure over a period of 2 or 3 hours on condition our lamp is stable. Here you have an image of the lamp open so that you can see why it's called a hollow cathode. So this cylinder in the middle, this is acting as the cathode. And in our case, what we do is we place a cylinder made of pure neodymium in the center. We are running this lamp with currents up to 1 amp, voltage is up to 2 kilovolts, and it has to be water refrigerated, basically, because if not, it would melt. And we can get temperatures here up to 5,000 Kelvin. Later on in the poster session, Pratyush will be speaking about some modifications that we are doing in our lamp to improve the discharge and to improve the characteristics of the light that we obtain for neodymium. So please feel free to ask him as many questions. I'm sure he'll be very happy to answer. And finally, what we get from these lamps is this. So good spectra that we calibrate in intensity, also in wavelength. And finally, we have to fit every of those spectral lines that we are interested in to mathematical functions, depending on which is the main broadening mechanism, which in the case of the hollow cathode lamp is Doppler broadening. And not only we measure the atomic data, we are very careful when obtaining also the uncertainty of our atomic data, which is essential when we give this data, especially if we want our data to end up in databases. So we take into account basically every possible source of uncertainty that is affecting our measurements. And finally, I would like to do a bit of advertising and inviting all of you to the School on Atomic and Molecular Data Evaluation and Curation that we are organizing. This is the second edition. We'll be organizing it in September in Spain in our university. And this is a school that we do in conjunction with people from NIST and from the International Atomic Energy Agency and Imperial College London. So especially for PhD students and early career researchers, postdocs, we think this is a very good moment to interact, learn new things, and also expand your collaborations. So thank you very much. And any questions, I'll be very happy to answer.